Today we talk about calculus. We also start from one proposition. Previous day we also discussed definition of derivative in higher domain, that means in Rn. Now we also going to some proposition. Let f C subset of Rn to Rm be a function such that f is differentiable at C belongs to interior of C, then f is continuous. So you have to show that f is continuous. Since f is differentiable at point C and C belongs to interior of C, then limit x tending to C, norm of fx difference fc difference f dash c x minus c norm by norm of x minus c equal to 0. Then we have to show that f is continuous at point C. Note that for x belongs to Rn, fx minus fc equal to fx minus fc minus f dash c x minus c plus f dash c x minus c. This equal to this less than equal to norm of fx minus fc minus f dash c x minus c plus norm of f dash c x minus c. Okay, now we write a equal to f dash c, then this one equal to norm of fx minus fc minus f dash c x minus c, norm of this multiplied by norm of x minus c plus norm of a x minus c. Okay, where a equal to f dash c. Then this equal to then limit x tending to c fx equal to fc. Why? Because this equal to f dash c and this tending to 0 as x tending to c. So limit x tending to c fx equal to fc. So f is continuous at c. Okay. Then what happened? We also proved this proposition. If f is differentiable at C belongs to interior of C, then fp continuous also. Now then we're also going to, that means here we erase this portion and going to another portion, collection of all linear operator from Rn to Rm. Okay, this one discussion by LRMRN. Now f of xy equal to xy by x square plus y square, where xy not equal to 0 0 and 0 if xy equal to 0 0. Okay, where f of r square to r then we know that f is not continuous at 0 0. We know that f is not continuous at 0 0. Okay, then then del f by del x 0 0 equal to limit x tending to 0 f of x 0 difference f of 0 0 by x equal to 0. Similarly, del f by del y of f of 0 0 equal to 0. This shows that f is not continuous, but partial derivatives are exist. F is not continuous, but partial derivatives are exist. From above theorem, f is not differentiable at 0 0. Hence, f is not differentiable at 0 0. Okay, so f is not continuous but partial derivative exists, but f is not differentiable at 0 0. Then relation between directional derivative and partial derivative, we have to find this relation. I also write one proposition. Where is this portion? I'm going to be write a proposition. Here proposition, let f C subset of Rn to Rm be a function such that f is differentiable at point C belongs to interior of C, then f dash Cu equal to Au for all A belongs to Rn. Okay, now we're going to prove of this proposition. Let f dash C equal to A, since C belongs to interior of C and there exists R greater than 0 such that VRC subset of interior of C and C plus H belongs to BRC where norm of H less than R. Okay, then let epsilon greater than 0 be given. Then there exists delta. Delta equal to epsilon c greater than 0 with delta less than r, such that norm of f of c plus h difference f of c difference ah less than epsilon norm of h for h belongs to Rn with norm h less than delta. Then norm of t equal to norm of h by norm of u, where u not equal to 0. Okay, hence from 1 norm of f of c plus h difference f of c difference tau less than epsilon norm of t norm of u for all t less than delta y norm u. Okay, this implies norm of f of c plus h difference f of c by t difference au less than epsilon norm of u for all t belongs to delta y norm u. Okay, then we erase our portion. Norm of f of c plus tu difference f of c by t difference a of u less than epsilon norm of u for all t less than delta y norm of u. So what we then f dash cu equal to limit t tending to 0 f of c plus tu difference f of c by t equal to au. Okay, so we also see that if be differentiable at a point c, then f dash cu equal to au. Okay, next we're going to another theorem. Some example we now write, then obviously going to first we see some example. Okay, Then we're going to another proposition and discussion about this relation between partial derivative and directional derivative. Okay, also erase this, not erase. Now we also write some example because some place is here, so write examples. If r squared to r given by f of xy, f of xy equal to xy by square root of x square plus y square, where xy not equal to 0 0 and 0 if xy equal to 0 0. Let c equal to 0, let c equal to 0 0, for u equal to u1 u2 not equal to 0 0, then f of u dash c equal to limit t tending to 0, limit t tending to 0, f of c plus ut difference f of c by t. Okay, then we write here, f of limit t tending to 0, limit t tending to 0, f of u1t u2t divided by t equal to limit t tending to 0 t square u1 u2 by t norm t root over of u square plus u1 square plus u2 square equal to limit t tending to 0 t u1 u2 by norm t square root of u1 square u2 square does not exist, does not exist. Okay, if u1 u2 not equal to 0 0, then directional derivative does not exist and hence f is not differentiable at c. So f is not differentiable at c. Okay, now we erase this portion, then going to discussion of another one. Now we also define if r squared to r, define if r squared to r as if xy equal to x square y divided by x square y square, where xy not equal to 0 0 and obviously 0 where xy equal to 0 0. at c equal to 0 0, and for u equal to u1 u2 not equal to 0 0, if just cu equal to limit t tending to 0, f of u1 t u2 t divided by t. Okay, then this one equal to limit t tending to 0, t square u1 square t u2 divided by t norm t square root of u1 square u2 square, okay, equal to 0. Thus f dash cu equal to au for u belongs to r square, and so f dash c equal to a. Okay, now we also discuss another example. Here if r square to r, f of xy equal to x cube y divided by x to the power 4y square, where xy not equal to 0 0. At point 0 0, u equal to u1 u2 not equal to 0 0 belongs to r square, f dash cu equal to limit t tending to 0, f of c plus t u difference f of c by t. This one equal to limit t tending to 0 0, f of u1 t u2 t by t. Okay, then this implies that limit t tending to 0, u1 cube u2 t to the power 5 divided by t to the power 5 u1 to the power 4 plus u2 square. Okay, then this one equal to, we erase our portion, this one equal to limit t tending to 0, u1 cube u2 divided by u1 to the power 4 u2 square does not exist. Okay, so next we're going to another example. Okay, we're also going to another example. We erase this portion and going to another example. Okay, so We also write f of xy equal to x cube y divided by x to the power 4 y square. If xy not equal to 0, 0. Then what happened? Then obviously we write c equal to 0, 0 and f dash cu equal to limit t tending to 0 f of tu t u1 u2 difference 0 phi t equal to what? Equal to limit t tending to 0. Then this equal to 0. Okay, then thus f dash cu exists for all values of f, for all values of f, and f dash cu equal to au equal to 0 for all u belongs to r square. Then f dash cu be a linear operator, be a linear operator. Okay, now we're going to let h equal to h1 h2 and belongs to r square with h not equal to 0. Then what happened? Then limit norm of h tends to 0 f of c plus h difference f of c difference ah by norm of h equal to limit norm of h tends to 0 f of h1 h2 divided by square root of h1 square h2 square. Then limit norm of h tends to 0 as norm of h1 cube norm of h2 divided by norm of h1 to the power 4 and h2 square root of h1 square h2 square. Okay, then what happened? Then this one equal to limit norm of h tends to 0 h2 equal to h1 square. Here we write h1 cube and h1 square divided by h1 to the power 4 h1 to the power 4 square root of h1 square and h1 to the power 4. Then what happened? then happen limit norm h tends to 0. Here above is 1, below is 2, square root of 1 plus h1 square. This one. Okay, this equal to half, not equal to 0. Okay, so f is not differentiable at 0 0. So what happened? So f is not differentiable at 0 0. Okay, so we also discuss three examples and also see that one proposition and as obviously another example, and obviously if differentiable then continuous. And now we also discuss two important proposition which shows that relation between partial derivative and directional derivative. But today we stop here. In next class we also discuss that.